The moment it happens, no one sees it. No splash. No dramatic slow motion. Just silence. A whale that once ruled the sunlit surface, a titan of muscle and blubber and bad attitudes toward boats, begins its final descent. Down it drifts, through water that grows colder, darker, and heavier by the second. This is not a fall so much as a surrender. Gravity takes the wheel. The deep ocean waits below, like an empty city at night, lights off, streets abandoned, holding its breath. If this gentle exploration of the strange ecosystems formed by ocean food falls helps you unwind tonight, please like the video, subscribe to the Deep Sea Documentary channel, and leave a comment sharing when and where you're listening, so this calm science can reach more people who drift off to sleep beneath the ocean's depths. Now, lie back, relax, and enjoy today's video. For thousands of meters, nothing interrupts the journey. The whale passes layers of water that once buzzed with life and sound, then slips into a realm where sunlight has never been invited and pressure is measured in crushed submarines per square inch. Down here, the seafloor is mostly quiet. It is not lifeless, but it is restrained. Food is scarce. Every meal is a surprise guest, and most days, nobody shows up. The animals that live here are masters of patience. They have learned the art of waiting without hope, which is a useful skill when dinner might arrive once a year or once a decade. Then the whale arrives. When its massive body finally meets the seabed, it does not explode or scatter. It settles. Soft sediment puffs outward like a sigh. And in that moment, the rules of this place change. What was once a nutritional desert becomes a sudden jackpot. Imagine living in a town where it rains pennies once every 10 years, and then one day, a fully stocked grocery store drops out of the sky. That is the scale of this event. The deep sea does not do small reactions. News travels fast without sound. Chemical signals bloom outward through the water and sediment. Invisible announcements that say only one thing. Something enormous has died. And in the deep ocean, death is not a tragedy. It is a headline. It is an opportunity. It is the closest thing this ecosystem has to a holiday. Within hours or days, shapes begin to emerge from the darkness. Shadows with teeth. Bodies built for efficiency, not elegance. They arrive calmly, not in a frenzy, because no one needs to rush. And a single whale contains more food than most deep-sea creatures will see in several lifetimes. There is time. There is plenty. The ocean floor, normally quiet enough to hear your own existential dread, becomes crowded with movement. What makes this moment so strange is not just the abundance, but the contrast. The deep sea is defined by limits. Limited energy, limited growth, limited second chances. And yet here lies a gift so large, it bends the entire system around it. The whale does not just feed individuals, it feeds processes. It feeds chemistry. It feeds futures. This one body becomes an anchor point for life in a place where life is usually spread thin like butter scraped over an abyss. From a storytelling perspective, this is where the deep ocean breaks character. It stops being slow and stoic and briefly becomes dramatic. The seafloor transforms into a stage where creatures that are normally invisible step into the spotlight. This is not chaos. It is choreography refined by millions of years of waiting for this exact moment. Everyone knows their role. Everyone knows when to arrive, The whale is not just food, it is a signal flare in the dark. There is also something deeply poetic about it. A whale spends its life travelling vast distances, stitching together ecosystems at the surface, and when it dies, it performs one final migration, delivering all that stored energy to the deepest parts of the planet. It is a vertical journey instead of a horizontal one. The whale becomes a bridge between worlds that almost never touch. Sunlight and darkness, motion and stillness, abundance and scarcity. And somehow, this is all happening in total silence. No applause, no soundtrack, just jaws, bacteria, bones, and time. If the deep sea could laugh, this would be the moment it chuckles and says, "See, I told you I was busy down here." This is why ocean food falls are so fascinating. They are not just events, they are transformations. They reveal that even in Earth's most extreme environments, life is not merely surviving. It is waiting for gravity to deliver a miracle wrapped in blubber, waiting for a dinner party so exclusive that it only happens when a giant dies. And as strange as it sounds, this is not a story about death. It is a story about what happens after. About how the deep ocean, patient and resourceful, turns loss into opportunity. Because down here, nothing is wasted, not even a giant. To understand ocean food falls, you have to first understand just how unfair the deep sea is. Down there, life exists on a strict budget. Sunlight never shows up, plants never grow, and the idea of a daily meal is considered wildly optimistic. Most deep-sea animals survive on a slow drizzle of organic debris that sinks from the surface like nutritional dust. It is not glamorous. It is more like licking crumbs off the floor and calling it a lifestyle. This is where food falls come in. An ocean food fall is exactly what it sounds like. A large package of organic material that sinks from above and lands on the seafloor, delivering a sudden, concentrated pulse of energy. Think of it as the opposite of fast food. It takes days, weeks, or months to arrive, but when it does, it feeds everyone within reach. In the deep sea, gravity is the delivery driver, and it never asks for directions. Food falls come in many forms, and not all of them are dramatic. Some are quiet and leafy. Massive mats of kelp can tear loose from coastal forests during storms and drift out to sea. Over time, they become waterlogged, lose buoyancy, and begin their slow descent. When they reach the bottom, they provide a compact salad bar for deep-sea life that is otherwise unfamiliar with vegetables. It is not glamorous, but it is appreciated. Then there are the medium-sized falls. Dead fish, squid, and jellyfish sink regularly, especially after spawning events or seasonal die-offs. These are the everyday meals of the deep ocean, the equivalent of finding a dropped sandwich on the sidewalk. Not life-changing, but definitely worth stopping for. These smaller falls are short-lived, often consumed quickly, leaving little trace behind. At the extreme end of the spectrum are the giants. Large sharks, massive rays, and of course, whales. These are not meals, these are events. A single large carcass contains more energy than most deep-sea communities see in years. When one arrives, it fundamentally alters the local environment, not just feeding animals, but reshaping how nutrients move through the system. What unites all food falls is the way they bypass the usual limitations of deep-sea life. Instead of energy trickling down molecule by molecule, it arrives all at once, wrapped in flesh, fat, and structural complexity. Bones, skin, connective tissue, and lipids all break down at different rates, creating a layered resource that can support different organisms over time. In other words, food falls are not just meals. They are temporary ecosystems in a box. Another key feature of food falls is unpredictability. No deep-sea animal can rely on one arriving on schedule. There are no calendars in the abyss. This randomness has shaped life in profound ways. Creatures that take advantage of food falls tend to be opportunistic, capable of detecting chemical signals from far away and traveling long distances to investigate. When gravity sends a package, someone out there is always listening for the delivery notification. The physics of sinking also matters. As organic material descends, it is altered by pressure, temperature, and scavengers in the water column. By the time it reaches the bottom, it is often partially consumed, compressed, or reshaped. This means that food falls are not uniform. Each one is unique, depending on what fell, where it fell, and how long the journey took. The deep sea does not do standardized meals. Importantly, food falls connect surface ecosystems to the deep ocean in a direct, physical way. Everything that sinks once lived in sunlight. Kelp grew using solar energy. Fish fed on plankton. Whales stored years of surface productivity in their bodies. When these materials fall, they carry that energy straight into the dark. It is one of the few ways the deep sea gets a substantial taste of the surface world. In that sense, food falls act like biological messages in a bottle. They tell deep sea ecosystems what is happening far above. A bloom at the surface, a storm along the coast, a population boom or collapse. All of it eventually sinks, one way or another. Gravity does not discriminate, it just pulls. So when scientists talk about ocean food falls, they are not just describing dead things on the seafloor. They are describing a fundamental mechanism that keeps the deep ocean alive. Without these falling feasts, life in the abyss would be far more limited, far more isolated, and far more boring, which is scientifically unacceptable. In the deep sea, sunlight is a myth, photosynthesis is a rumor, and gravity is the only delivery service that actually shows up on time. For a long time, scientists believed the deep sea floor was mostly empty. Not completely lifeless, but sparse, quiet, and monotonous, like an abandoned parking lot with a few determined weeds growing through the cracks. This assumption made sense. Before modern technology, the deep ocean was almost impossible to observe directly. Nets came back with strange creatures, sure, but they told no stories about where those animals lived or what they were doing before they were rudely dragged into daylight. The idea that something as large and dramatic as a whale carcass could regularly reach the seafloor and support complex communities simply did not occur to anyone. Whales were surface giants. Their deaths were assumed to be surface events too, scavenged by sharks or decomposed long before sinking. The deep sea, in this view, was a place of eternal famine, not feasting. That story began to crack in the late 20th century, when deep-sea exploration technology finally caught up with human curiosity. Submersibles and remotely operated vehicles gave scientists eyes on the seafloor for the first time. And when you actually look at the deep ocean, instead of guessing about it, it turns out it has opinions. One of the earliest turning points came when researchers investigating the seafloor stumbled across massive skeletons lying in the mud. Not fossils, not rocks, bones, big ones. The kind that do not belong to fish or squids, or anything that lives permanently in the deep. These were unmistakably whale remains, and they were not alone. Around them were dense clusters of organisms, far more abundant than anything typically seen at those depths. At first, these discoveries were confusing. The bones looked ancient, but the surrounding life looked active. There were animals living directly on and around the skeletons, as if the whale had died yesterday. The seafloor, previously imagined as nutritionally starved, suddenly appeared capable of supporting thriving, localized communities. The parking lot had food trucks. And they had been there for years. As more whale falls were documented, a pattern emerged. These were not rare accidents. They were recurring features of the deep ocean. Whales have existed in large numbers for millions of years, and their sheer size means that when they die, sinking is not a question of if, but when. Over evolutionary time, this steady reign of giants quietly shaped life on the seafloor. Studying whale falls, however, is not simple. You cannot schedule one. Scientists either have to find them by chance or create them intentionally. Both approaches come with challenges. Finding a natural whale fall is like looking for a specific couch cushion in a warehouse the size of a continent. But sometimes, curiosity gets lucky. Once a whale fall is located, researchers use submersibles to observe, sample, and document the site over time. These dives are slow, meticulous, and expensive. Every minute on the seafloor matters. Scientists map the bones, collect surrounding sediments, and catalogue the species present. Over repeated visits, they can track how the community changes, revealing that these are not static graveyards, but dynamic systems that evolve for years, or even decades. In some cases, researchers have taken a more proactive approach. Whale carcasses have been intentionally placed on the seafloor to study what happens next. This involves logistical feats that are equal parts science and extreme furniture moving. A multi-ton body must be transported offshore, carefully lowered and positioned without drifting away. It is one of the few scientific experiments where the test subject is both enormous and already dead. What these studies revealed was revolutionary. The deep sea floor was not uniformly barren. Instead, it was punctuated by hotspots of activity, each centered around a massive organic input. Whale falls acted like long-term oases, supporting specialized species that were rarely seen anywhere else. Some organisms appeared to be entirely dependent on these events, suggesting a hidden layer of biodiversity that had gone unnoticed. This forced scientists to rethink how energy moves through the ocean. The deep sea was no longer just a passive recipient of sinking debris. It was an active landscape shaped by episodic abundance. Whale falls were not anomalies. They were part of the system's design. Perhaps the most humbling realization was how much had been missed, simply because no one had looked closely enough. For decades, the deep ocean was described using absence, lack of light, lack of food, lack of life. Whale falls flipped that narrative. They showed that even in the most extreme environments, life finds ways to organize, specialize, and thrive, given the right opportunity. In hindsight, it seems obvious. Drop a mountain of food into a starving world, and something interesting will happen. But science often advances not by obvious ideas, but by the moment when someone finally sees what has been there all along. The deep sea floor was never empty. It was just quietly waiting for a whale to fall and for humans to notice. When a massive carcass settles onto the deep sea floor, the clock starts ticking. Not because the food will run out anytime soon, but because the first wave of diners has a very specific job to do. This is the scavenger stage, and it begins fast, loud, and unapologetically messy. If the deep sea had a demolition crew, this would be it. The arrival of scavengers is triggered by chemistry, not sight. In total darkness, smell is everything. As the whale's tissues begin to break down, chemical compounds leak into the surrounding water, spreading outward like an invisible beacon. Deep-sea scavengers are exquisitely tuned to these signals. Some can detect them from kilometers away, which is impressive considering they are essentially sniffing for dinner in a planet-sized void. The first to arrive are usually large, mobile predators and scavengers capable of covering long distances. Sleeper sharks glide in with the patience of creatures that know the meal is not going anywhere. These sharks are slow, cold-adapted, and built for efficiency rather than speed. They do not rush. They circle, they assess, and then they start removing flesh in massive, deliberate bites, carving into blubber that once insulated a living giant. Hagfish soon join the chaos, and if sharks are the heavy machinery, hagfish are the plumbing problem no one asked for. These jawless fish look like someone crossed an eel with a nightmare and then forgot to finish the design. Hagfish do not bite chunks off the carcass. They do something far more unsettling. They burrow inside it. Using a combination of slime, leverage, and deeply questionable life choices, they tie themselves in knots to rip flesh from the inside out. This internal feeding is incredibly effective. Hagfish can hollow out large sections of tissue, leaving behind skin and connective structures that collapse inward. They turn solid muscle into a collapsing cave system, accelerating the breakdown of the carcass. It is not pretty, but the deep sea is not here to impress anyone. Other scavengers pile in as well. Large crustaceans scuttle across the bones. Deep-sea fish with expandable jaws dart in to grab loose scraps. Each species has a slightly different feeding strategy, and together they dismantle the soft tissues with industrial efficiency. What would take decades to decompose naturally is reduced to exposed bone in months or even weeks. Despite the frenzy, this stage is surprisingly orderly. There is no fighting, no hoarding, no dramatic confrontations. The sheer abundance of food removes competition. Everyone eats. There is no need to defend territory when the buffet stretches for meters. In the deep sea, aggression is expensive, and this meal is too big to waste energy on drama. The scavenger stage dramatically reshapes the carcass. Blubber disappears first, followed by muscle. Skin sloughs away. Ligaments loosen. Massive bones that once supported tons of muscle are slowly freed and repositioned as the body collapses under its own weight. What was once a recognizable animal becomes an open framework of skeleton and sediment. This process also has a physical impact on the surrounding environment. As scavengers feed, they stir up sediments, redistribute organic matter, and oxygenate patches of seafloor that are normally undisturbed. The area around the carcass becomes a zone of intense biological activity, temporarily altering conditions in ways that affect which organisms can settle there later. One of the most fascinating aspects of this stage is its speed. The deep sea is often described as slow, but scavengers waste no time. Evolution has favored creatures that can exploit rare opportunities quickly and efficiently. When something this large arrives, hesitation is not rewarded. The first wave does the heavy lifting, literally and figuratively. And then, just as suddenly as it began, the scavenger stage winds down. Not because the food is gone, but because the type of food has changed. Once the soft tissues are mostly removed, the large scavengers lose interest. There is no blubber left to carve, no easy calories to slurp. The sharks drift away. The hagfish retreat, leaving behind slime, sediments, and a skeleton that now tells a different story. This transition marks a shift in ownership. The carcass has been stripped to its structural core, and what remains is no longer attractive to the original crew. The professional cleaners have finished their job, left no receipt, and moved on to the next call. What they leave behind is not emptiness, but potential. Exposed bones, rich in stored energy. Altered sediments primed for colonization. A foundation upon which entirely different communities will build. The scavenger stage is not the end of the story. It is the opening act, loud and efficient, clearing the stage for what comes next. In the deep sea, even demolition is part of construction. Once the loud eaters leave, the deep sea does not go quiet. It gets busy in a different way. The massive carcass is no longer a feast of flesh, but the surrounding seafloor has been permanently changed. During the frenzy of the scavenger stage, enormous amounts of organic material were shredded, scattered, and pressed into the sediment. Oils seeped downward. Tiny fragments of tissue settled like nutritional confetti. What was once ordinary mud is now enriched, and in the deep sea, enriched mud is luxury real estate. This is the beginning of the enrichment opportunist stage. It is less dramatic than the arrival of sharks, but far more crowded. Instead of large animals tearing at meat, the focus shifts to creatures that specialize in exploiting nutrient-loaded sediments. They do not care about bones, they care about what has soaked into the ground. Polychaete worms are among the first to move in. These segmented worms are experts at sensing chemical changes in sediment. Where the mud is rich, they burrow. Some extend feathery appendages into the water to collect particles, while others ingest sediment directly, extracting every usable molecule as it passes through their bodies. It is not glamorous dining, but it is thorough. If nutrients were money, these worms would be running forensic audits. Crustaceans follow close behind. Small amphipods, isopods, and other jointed scavengers crawl and burrow through the enriched zone, feeding on microbial films and organic debris. Their activity churns the sediment, mixing oxygen downward and nutrients upward. This constant reworking turns the seafloor into a living compost heap, accelerating biological processing in ways that ripple outward from the carcass. Snails and other mollusks join the scene, grazing across surfaces that are now coated in microbial growth. To them, the area around the remains is not a graveyard. It is a pasture. They scrape, rasp, and vacuum their way across the seafloor, converting microscopic productivity into slow, steady growth. What makes this stage so important is its spatial reach. Unlike the scavenger stage, which is concentrated directly on the carcass, enrichment spreads. Nutrients leach outward, creating a halo of productivity that can extend meters beyond the original site. This transforms a small patch of the deep ocean into a hotspot of biological activity, increasing local diversity and abundance. These opportunists are not specialized for whale falls alone. Many of them exist throughout the deep sea, surviving on whatever organic matter they can find. But when enrichment occurs, they respond rapidly, reproducing faster, growing larger, and crowding into the area. It is a temporary boomtown, and everyone is trying to cash in before conditions return to normal. The pace of life here is still slow by surface standards, but relative to the deep sea, it is a frenzy. Worms reproduce, crustaceans molt. Snails expand their grazing ranges. The sediment itself becomes layered with burrows and feeding trails, physical records of biological activity that can persist long after the animals move on. This stage also plays a crucial role in recycling. By breaking down organic material in the sediment, opportunists convert complex compounds into simpler forms that can be used by microbes and other organisms. Energy is not just consumed, it is transformed and redistributed. The carcass may be gone, but its influence spreads through the ecosystem, molecule by molecule. There is something almost ironic about this stage. The deep sea is often portrayed as static and unchanging, yet here is a scene of rapid ecological response. A single event alters the landscape, and life pours in to take advantage. It is proof that even in the most extreme environments, ecosystems are flexible, responsive, and opportunistic when given the chance. Eventually, however, the enrichment begins to fade. The easily accessible nutrients are consumed. Sediment chemistry shifts back toward baseline conditions. Populations thin out. The boom ends. Some opportunists remain, but many move on or die off, their bodies adding one last layer of organic matter to the system. What remains is a seafloor that has been fundamentally altered by the event. The sediment has been reworked, nutrients have been cycled. Energy has flowed through dozens of species that would otherwise never have encountered such abundance. The carcass has already played multiple roles, and it is not done yet. The enrichment opportunist stage is a reminder that ecosystems are not defined solely by their largest players. After the giants leave, the small and persistent take over. They do not make headlines, but they do the work that turns sudden abundance into lasting ecological impact. In the deep sea, even the mud gets its moment in the spotlight, long after the last scraps of soft tissue are gone and the surrounding sediment has been thoroughly picked over. The whale fall enters its strangest phase. At this point, what remains looks deceptively simple. A skeleton resting on the seafloor, pale bones half buried in mud. To the untrained eye, it might seem like the party is over. In reality, this is when things get truly weird. Whale bones are not just structural leftovers, they are biochemical vaults. Inside them is a dense store of lipids, especially in large species, built up over years of life to provide buoyancy and energy. These fats are stubborn. They do not disappear quickly. And when they begin to break down, they trigger a cascade of chemical reactions that fundamentally reshape the local environment. The key players in this stage are bacteria, anaerobic bacteria, to be precise. These microbes thrive in oxygen-poor conditions and specialize in breaking down complex organic molecules. As they digest the lipids trapped within the bones, they produce hydrogen sulfide as a byproduct. This gas smells like rotten eggs, is toxic to most animals, and would normally be considered a terrible idea to build a lifestyle around. The deep sea, however, sees hydrogen sulfide and thinks, opportunity. As sulfide concentrations increase around the bones, the whale fall becomes chemically similar to environments like hydrothermal vents and cold seeps. These are places where life is fueled not by sunlight, but by chemical energy. This is the sulfophilic stage, named for organisms that love sulfur in the same way most life prefers oxygen, which is to say, enthusiastically, and with zero concern for human comfort. Microbial mats begin to coat the bones and surrounding sediments, forming pale, filamentous layers that quietly churn through chemical reactions. These microbes use sulfide as an energy source, converting it into biomass. They are not just decomposers anymore. They are primary producers, forming the base of an entirely new food web in total darkness. Animals that thrive in this stage are unlike the opportunists that came before. Many are highly specialized, having evolved traits specifically for living in sulfide-rich environments. Some host symbiotic bacteria within their tissues, effectively outsourcing their digestion to microbes that can process toxic chemicals. In return, the animals provide shelter and access to sulfide. It is a business partnership forged in poison. These organisms cluster directly on the bones, embedding themselves in cracks and cavities where sulfide production is strongest. To them, the skeleton is not a corpse. It is a power plant. Energy flows outward from the decaying lipids, fueling life that would otherwise be impossible at these depths. What makes this stage remarkable is its longevity. While earlier phases are relatively brief, the sulfophilic stage can persist for decades. As long as lipids remain in the bones, bacteria continue producing sulfide, and the chemical ecosystem remains active. This turns the whale fall into one of the longest-lasting sources of energy on the deep sea floor. The presence of sulfide also reshapes the surrounding sediment. Chemical gradients form, creating sharp boundaries between habitable and uninhabitable zones. Animals position themselves with precision, balancing access to energy against the risk of toxicity. It is ecological tightrope walking, and evolution has fine-tuned the act. From a broader perspective, this stage shattered long-held assumptions about the deep sea. It demonstrated that chemosynthetic ecosystems were not limited to rare geological features. Biological events alone, like the death of a whale, could create chemically driven communities in the middle of otherwise unremarkable seafloor. There is also something deeply counterintuitive about it. A skeleton, often associated with endings, becomes the foundation for one of the most productive phases of the entire process. Life does not just cling to the remains. It rewrites the rules of how energy enters the ecosystem. Eventually, even this stage winds down. The lipids are exhausted. Sulfide production slows. Microbial activity declines. The specialized animals disappear, leaving behind mineral-stained bones and altered sediments as evidence of what once occurred. The chemical factory shuts down, having run its course. But for years, sometimes decades, the whale fall exists as a pocket of chemical rebellion in the deep sea, a place where toxic gas fuels life, bacteria run the economy, and bones become batteries. In a world without sunlight, common sense is optional. If you were tasked with designing an animal to eat bones, you would probably start with teeth, or at least a mouth. Evolution, however, looked at that idea, shrugged, and decided to try something much stranger. Enter the bone-eating worms, organisms so bizarre that they feel less like animals and more like biological loopholes. These worms belong to a group that only came to scientific attention relatively recently, and they are found almost exclusively on the bones of large marine animals resting on the seafloor. Their lifestyle is highly specific. They do not scavenge flesh. They do not burrow through sediment. They wait for skeletons, and when they find one, they move in with unsettling enthusiasm. At first glance, a bone-eating worm looks fairly unremarkable. A slender body, a feathery plume at one end, and no obvious signs of danger. Then you notice something missing. There is no mouth, no gut opening, no obvious way for food to go in. For an animal whose entire existence revolves around eating bones, this seems like a design flaw of the highest order. The secret lies in the other end of the body. Instead of a mouth, these worms grow root-like structures that penetrate directly into the bone. These roots secrete acids that dissolve the hard mineral matrix, allowing the worm to access the organic compounds locked inside. It is less like chewing and more like mining. The worm does not bite the bone. It chemically persuades it to fall apart. Once inside, symbiotic bacteria take over. These microbes live within the worm's tissues and do the actual work of breaking down complex molecules. The worm provides access and infrastructure. The bacteria provide digestion. Together, they form a tiny, highly specialized refinery built for one purpose and one purpose only: turning skeleton into sustenance. This relationship is so tightly integrated that neither partner could survive alone in this context. The worm depends entirely on its bacterial tenants for nutrition, and the bacteria depend on the worm for access to the bone environment. It is less a partnership and more a biological merger. Bone-eating worms also display extreme sexual dimorphism, which is a polite way of saying the males are tiny and weird. Females grow large enough to embed themselves deeply into bones, while males are microscopic by comparison, often living inside the tubes of females. Their primary role appears to be reproductive, which in evolutionary terms is both efficient and deeply humbling. Reproduction is a numbers game. Females release larvae into the water, where they drift until they encounter suitable bone. This is not an easy task in the vastness of the deep sea, which makes the success of these worms all the more remarkable. They have evolved to exploit a resource that is rare, unpredictable, and temporary, yet they do it consistently enough to sustain entire populations. Their presence accelerates the breakdown of bones dramatically. By boring into the skeleton, they increase surface area, enhance microbial access, and speed up the release of stored nutrients. In effect, they act as biological locksmiths, opening vaults that would otherwise take far longer to crack. What makes bone-eating worms particularly fascinating is what they reveal about evolution's flexibility. There is no rule that says animals must have mouths. There is no requirement that digestion happen internally in the way we expect. Given the right conditions and enough time, life will find solutions that look ridiculous until you realize they work perfectly. These worms also challenge our ideas of specialization. Their entire existence is built around a single resource. Take away the bones, and they have no backup plan. But in an environment where whale falls have occurred for millions of years, that specialization makes sense. Evolution does not care about versatility if reliability is good enough. From a human perspective, bone-eating worms are unsettling. They reduce massive skeletons to fragile remnants, silently and efficiently, without ever taking a bite. From the perspective of the deep sea, they are simply doing their job, one dissolved femur at a time. In the end, these worms are not evolutionary accidents. They are proof that life will exploit every niche available, even ones that require dissolving a skeleton from the inside without a mouth. If that sounds absurd, it is only because evolution has a much better sense of humor than we do. If the deep sea had a ruling class, it would not be sharks, worms, or anything with eyes. It would be microbes. Tiny, unseen, and spectacularly busy. Microbes are the organisms that make ocean food falls matter long after the big animals leave. They do not announce their presence. They do not pose dramatically on camera. They simply get to work, rewriting the chemistry of the seafloor one molecule at a time. From the moment a carcass touches down, microbes begin their takeover. They are already everywhere, embedded in sediments, drifting in the water, clinging to particles. When a massive source of organic material arrives, they respond instantly, not by moving, but by multiplying. Their populations explode, forming dense communities that coat surfaces, infiltrate cracks, and seep into every available niche. If larger animals are the visible crowd at a food fall, microbes are the infrastructure beneath their feet. What microbes do best is conversion. Large pieces of organic matter are useless to most life unless they are broken down into smaller, accessible components. Microbes perform this breakdown with relentless efficiency. Proteins, fats, and complex compounds are dismantled into simpler molecules that can move through the ecosystem. Without this step, most of the energy locked inside a carcass would remain inaccessible, trapped in forms too complex for other organisms to use. In this way, microbes act as economic middlemen. They take raw material and turn it into currency. Nutrients are released into sediments and water, where they can be absorbed, exchanged, and reused. Every worm that feeds on enriched mud, every grazer that scrapes the surface, every slow-growing organism that settles nearby is benefiting from microbial labor it will never acknowledge. Microbial activity also shapes the physical environment. As they metabolize organic matter, they alter oxygen levels, acidity, and chemical gradients in the sediment. These changes determine which organisms can survive and where they can live. Boundaries form, shift, and dissolve, all dictated by microbial processes happening at scales too small to see but too powerful to ignore. One of the most remarkable aspects of microbial life at food falls is its adaptability. Different microbial communities dominate at different times, each responding to the changing availability of resources. As one energy source becomes scarce, another microbial group rises to prominence, ready to exploit whatever remains. This constant turnover ensures that very little goes to waste. In the deep sea, microbes are the ultimate recyclers, operating a zero-waste policy long before humans coined the phrase. They also provide stability. While larger animals come and go, microbial communities persist. They form the foundation upon which all other stages depend. Even when visible life thins out, microbes continue processing, quietly maintaining the flow of energy through the system. If a food fall is an ecosystem, microbes are the laws of physics that keep it functioning. What makes this role especially fascinating is how little direct attention microbes receive. Early studies of the deep ocean focused on animals large enough to see and catch. Microbes were acknowledged, but rarely celebrated. Only with advances in molecular techniques did their true influence become clear. Scientists began to realize that these invisible organisms were not just supporting players, but primary drivers of deep-sea ecology. Microbes also connect food falls to the broader ocean in subtle ways. The chemical byproducts of their metabolism diffuse into surrounding waters, influencing microbial communities beyond the immediate site. In this way, the impact of a single carcass can ripple outward, affecting areas that never physically touch it. Energy spreads not just through bodies, but through chemistry. There is something almost poetic about it. The largest animals on Earth ultimately depend on the smallest to complete their final contribution to the ecosystem. A whale's immense body is reduced, processed, and redistributed by organisms so small they can fit thousands on the head of a pin. Scale in the deep sea is relative. By the time a food fall has fully run its course, microbes have touched every part of it. They have mediated every transfer of energy, shaped every habitat, and determined how long the influence of the event will last. And when it is all over, when the bones are bare and the sediments settle, microbes remain, ready for the next delivery gravity sends their way. They do not need recognition. They already run the economy. The deep ocean is vast in a way that is difficult to truly grasp. It is not just big. It is empty in between the interesting parts. Hydrothermal vents and cold seeps, two of the most biologically rich environments on the seafloor, are scattered across this enormous landscape, like isolated cities, separated by thousands of kilometers of wilderness. For a long time, scientists struggled with a simple question. How do species that depend on these chemically fueled habitats manage to spread and survive when their homes are so far apart? The answer, it turns out, involves whales and gravity, and a surprisingly effective transportation network built entirely out of death. Food falls, especially large ones, create temporary habitats that closely resemble vents and seeps in key ways. They produce chemical energy. They support chemosynthetic microbes, and they persist long enough for specialized organisms to colonize, grow, and reproduce. In the middle of an otherwise inhospitable abyss, they act as biological rest stops, offering shelter and sustenance where there would otherwise be none. For species adapted to chemical energy sources, this matters enormously. Many vent and seep organisms cannot survive on the sparse, detritus-based nutrition that dominates most of the deep sea. Without stepping stones, populations would be trapped in isolated pockets, vulnerable to extinction. Food falls change that equation by providing intermediate habitats that bridge the gaps. Imagine trying to cross a desert where the only water sources are scattered oases. Without intermediate stops, the journey would be impossible. Food falls serve as those oases, allowing organisms to disperse gradually rather than in a single, impossible leap. Larvae released at one site can settle at a food fall, mature, and later produce offspring that continue the journey. This process unfolds over evolutionary timescales. No single organism makes the entire journey. Instead, populations slowly expand their range, one generation at a time, using food falls as temporary footholds. Over millions of years, this stepping stone model has helped shape the distribution of deep sea life, connecting ecosystems that would otherwise remain isolated. What makes this even more fascinating is the directionality of the process. Food falls do not form in predictable locations. They appear wherever gravity decides to drop a carcass. This randomness creates a shifting network of connections that changes over time. Some routes open, others disappear. Species that can take advantage of this uncertainty gain a powerful evolutionary advantage. There is growing evidence that some organisms found at vents and seeps share close relatives that specialize in food falls. These relationships suggest a shared evolutionary history, one in which ancestors moved between habitat types as opportunities arose. Rather than being locked into a single environment, life in the deep sea appears far more mobile and interconnected than once thought. This perspective reshapes how we view deep sea ecosystems. Instead of isolated islands, they form a dynamic network linked by episodic events. Food falls are not just local phenomena. They are part of a larger system that facilitates movement, gene flow, and long-term survival across the abyss. The analogy of a subway system is surprisingly accurate. Vents and seeps are major stations, bustling with life. Food falls are smaller stops that open and close without warning. Miss one, and the line might not run again for years, catch it, and suddenly new destinations become reachable. From an evolutionary standpoint, this system rewards patience and flexibility. Species that produce larvae capable of drifting long distances, settling quickly, and exploiting temporary resources are more likely to succeed. Over time, these traits become more common, shaping the life histories of deep-sea organisms in subtle but profound ways. It also highlights the importance of large animals in maintaining deep-sea connectivity. The presence of whales over geological time did more than influence surface ecosystems. Their deaths created pathways through the deep ocean, enabling life to move, adapt, and persist in a fragmented world. Remove the whales, and the map changes. Food falls. Remind us that ecosystems are not just collections of species. They are networks of interactions spread across space and time. A carcass falling today may influence the distribution of life millions of years from now. That is a staggering thought, and one that underscores how deeply interconnected Earth's systems truly are. In the deep sea, even bones can become bridges. One of the most misleading things about ocean food falls is how quickly they begin. A massive carcass arrives, scavengers appear almost immediately, and within months, the most obvious signs of abundance seem to fade. From the outside, it looks like a brief spectacle, a flash of activity in an otherwise slow world. But that impression misses the deeper story. Food falls are not moments, they are timelines. The life of a food fall unfolds across multiple tempos, each operating on its own clock. The initial phase is fast by deep-sea standards. Large mobile scavengers locate the carcass, consume the soft tissues and move on. This can happen in weeks or months, a blink of an eye, in an environment where many organisms measure change in decades. To human observers, this stage feels decisive, like the main event. But what follows stretches far beyond that first rush. The remnants of the carcass continue to influence the seafloor long after the dramatic feeding has ended. Organic material buried in sediment breaks down slowly. Chemical conditions shift and stabilize. Biological communities establish, mature, and eventually decline. Each of these processes unfolds at a pace dictated by depth, temperature, and chemistry. The deep ocean is cold, and cold slows everything. Chemical reactions proceed at a crawl. Microbial metabolism, while relentless, is not rapid. This means that resources introduced by a food fall persist far longer than they would in warmer, shallower environments. Energy is released gradually, sustaining life over extended periods rather than being consumed all at once. In some cases, the influence of a large food fall can last decades. Bones remain, continuing to support specialized communities long after all visible flesh has vanished. Sediments enriched by organic input retain altered chemical properties for years, shaping which organisms can live there. Even after biological activity declines, physical traces such as burrows and altered sediment layers remain as records of what occurred. This extended timescale has important ecological consequences. Long-lived food falls provide stability in an otherwise unpredictable environment. For organisms that depend on them, this stability is invaluable. It allows for slower growth, longer lifespans, and more reliable reproduction. In a world where food is usually scarce and fleeting, a persistent resource changes the rules. The long duration also means that multiple generations of organisms can benefit from a single event. A carcass that arrives today may still be influencing the ecosystem decades later. supporting life that did not exist when it first fell. In this way, food falls act as time capsules, carrying the impact of one moment far into the future. Understanding these timelines has changed how scientists think about deep-sea resilience. The deep ocean is often portrayed as fragile, easily disturbed by change. While this is true in many respects, food falls demonstrate a different kind of resilience, the ability to extract maximum value from rare opportunities. When something large arrives, the system does not waste it. It stretches it, slows it down, and integrates it into the fabric of the ecosystem. This perspective also highlights the cumulative impact of food falls over geological time. Individual events may be rare, but over millions of years they add up. The repeated introduction of large organic inputs has shaped sediment composition, species distributions, and evolutionary pathways. The deep sea we see today is, in part, the product of countless long decomposed meals. There is a lesson here that extends beyond marine science. In a world obsessed with immediacy, food falls remind us that impact is not always obvious or instantaneous. Some effects unfold slowly, quietly, and persistently, shaping systems in ways that only become visible with patience and perspective. By the time a food fall has fully run its course, it may no longer be recognizable as such. The bones crumble. The sediments blend back into the surrounding seafloor. Life moves on, but the influence remains, woven into the history of that place. In the deep sea, even leftovers refuse to hurry. Not every food fall arrives with the drama of a whale. Most of the time, the deep sea is fed by much smaller offerings. Individual fish, squid, jellyfish, and other mid-sized animals sink to the bottom every day, quietly and without ceremony. These smaller food falls do not reshape ecosystems for decades, but they are far more frequent, and in many ways, they are the backbone of deep-sea dining. A single fish carcass may seem insignificant compared to a whale, but in the deep ocean, size is relative. For many animals, one large fish represents a major windfall. Energy is scarce, and even modest inputs can trigger intense biological responses. When a fish hits the seafloor, it becomes the center of attention, at least for a little while. The first thing to understand about small food falls is their speed. Unlike large carcasses, which can persist for months or years, a fish or squid is usually consumed rapidly. Scavengers arrive quickly, often within hours. The meal is dismantled with impressive efficiency, leaving behind little more than bones or cartilage. This is fast food by abyssal standards. Despite their short lifespan, small food falls attract a surprisingly consistent set of customers. Many deep-sea species rely heavily on these events, timing their movements and feeding strategies around the expectation that something, somewhere, will eventually fall. They do not need to know where the next meal will land. They just need to be ready. Some animals patrol the seafloor, covering large areas in search of chemical signals. Others remain stationary, waiting for food to come to them. When it does, they respond with remarkable precision. In the deep sea, loyalty to a good cafe is not about ambience. It is about reliability. Smaller food falls also create intense, localized competition. Unlike whale falls, where abundance reduces conflict, fish-sized carcasses are just small enough to be worth fighting over. Speed matters. The first arrivals get the best portions. Latecomers may find only scraps or nothing at all. This has shaped behaviors that favor rapid detection and swift response. These events also influence daily life in the deep ocean. For animals living at these depths, feeding opportunities are unpredictable. Small food falls provide bursts of energy that can sustain individuals for long periods. A successful meal today may mean survival through weeks of scarcity. In this way, even brief events have outsized importance. Another fascinating aspect of small food falls is their role in distributing energy unevenly across the seafloor. Because they are frequent but scattered, they create a patchwork of opportunity. Some areas receive repeated inputs, while others remain relatively barren. This spatial variability contributes to differences in community structure and species abundance across the deep ocean. Unlike larger food falls, smaller ones rarely leave long-lasting physical traces. Once consumed, the seafloor quickly returns to its previous state. But biologically, the impact lingers. Animals that fed grow larger, reproduce, or survive longer than they otherwise would have. Energy moves through the system, even if the evidence disappears. These small falls also highlight the deep sea's reliance on surface ecosystems. Many of the fish and squid that sink originate in productive upper layers of the ocean. Their deaths deliver surface-derived energy to the depths, reinforcing the connection between worlds that rarely interact directly. Every sinking fish is a reminder that the deep sea is not isolated, just downstream. From a scientific perspective, small food falls are challenging to study precisely because they are so fleeting. They arrive and vanish quickly, often between observation windows. Yet their cumulative impact is enormous. Over time, countless small falls likely contribute more total energy to the deep sea floor than the occasional giant. There is something almost charming about their simplicity. No long-term community, no chemical revolutions, just a meal, shared or stolen, gone almost as soon as it arrives. And yet, without these brief pop-up cafes, many deep-sea animals would struggle to survive at all. In the abyss, even a single tuna can be unforgettable. One of the most counterintuitive discoveries about ocean food falls is not how much life they attract, but how different that life can be. For a long time, scientists assumed that food falls simply gathered familiar deep-sea species into one place, like a neighborhood block party. What they found instead was closer to a costume convention. Many of the organisms living on and around these sites were not just visitors. They were specialists, found almost nowhere else, and seemingly designed for this exact, deeply strange lifestyle. Food falls create environmental conditions that are rare and extreme, even by deep sea standards. High concentrations of organic material, unusual chemistry, and long-lasting hard surfaces appear suddenly in a world that usually offers none of those things. For evolution, this is an open invitation. Whenever a new niche appears, something eventually evolves to move in, unpack, and refuse to leave. Over time, food falls have become cradles of biodiversity, hosting species that exist only because these events happen. Some animals are so closely associated with skeletal remains that they are rarely observed anywhere else. To them, a pile of bones is not a temporary resource, it is an address. What drives this biodiversity is the sheer variety of microhabitats within a single food fall. The surface of bones offers hard substrate in a deep sea dominated by soft sediment. Cracks and cavities provide shelter. Chemical gradients create zones that favor different metabolic strategies. Even small differences in bone density or orientation can change which organisms settle where. One carcass becomes many neighborhoods, This complexity allows species to specialize without directly competing. Some organisms prefer the outer surfaces of bones. Others burrow into them. Some cluster where chemical byproducts are strongest, while others settle at the edges where conditions are less extreme. Instead of one dominant species taking over, many coexist by carving out narrow ecological roles. The result is a community that looks nothing like the surrounding seafloor. Species richness increases dramatically in a small area, often including organisms new to science. In fact, food falls have become some of the most productive sites for discovering previously unknown deep-sea species. It turns out that if you want to find life no one has seen before, you should probably check inside a skeleton. This biodiversity also challenges the idea that the deep sea is uniformly harsh and limiting. While it is true that resources are scarce, food falls show that when conditions allow, life diversifies rapidly. Given the right combination of energy, stability, and structure, evolution gets creative. There is also an element of isolation that fuels diversification. Food falls are patchy and unpredictable, meaning populations can become separated from one another for long periods. This isolation allows genetic differences to accumulate, eventually producing distinct species adapted to slightly different conditions. One skeleton here, another hundreds of kilometers away, and suddenly you have cousins who no longer recognize each other at family reunions. Importantly, these unique species are not evolutionary accidents. They represent successful strategies honed over millions of years. Their existence tells us that food falls are not just feeding events, but evolutionary engines, generating new forms of life in the darkest parts of the ocean. From a conservation perspective, this hidden biodiversity matters. If food falls disappear or become less frequent, these specialized species have nowhere else to go. Their entire existence depends on a process that happens out of sight and out of mind. Protecting surface ecosystems and large marine animals is not just about saving charismatic species. It is about preserving the unseen diversity that depends on them. There is something oddly comforting about this. Even in a place defined by scarcity, life finds ways to diversify, adapt, and flourish in the most unlikely settings. A skeleton on the seafloor becomes a haven, a nursery, a community centre. Against all odds, it becomes home. In the deep sea, biodiversity does not always bloom in coral reefs or lush forests. Sometimes it blooms on bones. Life around ocean food falls is not gentle, and the organisms that thrive there wear that reality in their anatomy. These environments are defined by extremes: sudden abundance followed by long waiting periods, toxic chemistry alongside valuable energy, and intense competition compressed into small areas. To survive here, evolution has not played it safe. It has experimented, improvised, and occasionally gone completely off the rails. One of the most obvious adaptations is scale. Many animals associated with food falls possess disproportionately large jaws, expandable mouths, or distensible stomachs. When food is rare most of the time, but overwhelming when it appears. The best strategy is to eat as much as possible, as fast as possible. Subtlety is not rewarded. Capacity is. Some species can swallow chunks of food nearly as large as themselves, storing energy that may have to last months or years. Mobility is another key adaptation. Animals that exploit food falls often have the ability to travel long distances efficiently. Slow, energy-conserving movement allows them to patrol wide areas of seafloor without exhausting limited reserves. When chemical cues signal opportunity, they can respond without needing speed. Endurance matters more than acceleration. Sensing adaptations are especially refined, In total darkness, vision is optional, but chemical detection is essential. Many species have highly sensitive chemoreceptors that allow them to detect trace amounts of organic compounds released by decaying material. These sensors act like long-range antennas, guiding animals toward food they cannot see and may never have encountered before. Then, there are the adaptations required to tolerate conditions that would kill most life. Food falls create chemically hostile microenvironments with low oxygen and high concentrations of compounds that interfere with cellular processes. Animals living here have evolved tissues that can resist or neutralize these conditions. Some possess specialized proteins that protect cells from damage. Others regulate internal chemistry with precision, maintaining balance in places where the surrounding environment has none. Structural adaptations also play a role. Hard surfaces are rare in much of the deep sea, so when they appear, organisms that can cling, anchor, or embed themselves gain an advantage. Modified appendages, adhesive structures, and burrowing capabilities allow animals to hold position against currents or competitors. In a crowded environment, staying put can be just as important as arriving first. Reproductive strategies are equally specialized. Because food falls are temporary and unpredictable, many associated species produce large numbers of offspring, increasing the chances that some will encounter suitable conditions. Others time reproduction to coincide with resource availability, ensuring that young have access to food when it matters most. There is no single solution, only variations on a theme of uncertainty. One of the most fascinating aspects of these adaptations is how they reflect trade-offs. Specialization for food falls often means reduced ability to survive elsewhere. Traits that are advantageous in one context can be liabilities in another. Large jaws require energy to maintain. Chemical resistance can come at the cost of slower growth. Evolution balances these costs against the rewards of exploiting a rare but valuable niche. The result is a collection of organisms that look and function unlike anything found in more stable environments. They are not optimized for beauty or efficiency in a general sense. They are optimized for chaos, for unpredictability, for brief windows of opportunity surrounded by long stretches of scarcity. From a broader perspective, these adaptations highlight the creativity of natural selection. Given enough time and pressure, life will explore solutions that seem improbable or excessive. In the deep sea, where constraints are severe and mistakes are costly, those solutions become refined, repeated, and passed on. Food falls act as testing grounds for these innovations. Traits that succeed are reinforced. Those that fail disappear quietly into the sediment. Over millions of years, this process has produced a suite of adaptations that push the boundaries of what we consider possible for animal life. In the end, the creatures around food falls are not oddities. They are proof of concept. Proof that life can adapt to almost any set of rules, no matter how strange. And if those adaptations happen to look a little unhinged, that is simply evolution enjoying itself. In the sunlit world, life runs on photons. Plants capture light, convert it into chemical energy, and everything else rides that wave. In the deep sea, that system collapses completely. No light reaches these depths. Photosynthesis is not just difficult, it is impossible. And yet life persists, powered by an entirely different set of rules. At food falls, Those rules are written in chemistry. When a large organism dies and sinks, its body becomes a complex chemical package. Fats, proteins, and other organic compounds arrive intact, concentrated, and ready to be dismantled. This is not just food in the traditional sense. It is stored energy waiting to be unlocked by the right reactions. The breakdown begins almost immediately. Proteins, long chains of amino acids, are among the first to be targeted. Microorganisms cleave these chains into smaller components, releasing nitrogen-rich compounds into the surrounding environment. These compounds become valuable resources for other organisms, supporting growth and reproduction in a place where such nutrients are normally scarce. Fats tell a different story. Lipids are energy-dense and chemically stubborn. They resist degradation, which makes them ideal long-term fuel sources. When fats begin to break down under low oxygen conditions, they enter pathways that produce reduced chemical compounds. These compounds do not just drift away, they accumulate, reshaping the chemical landscape around the remains. This is where sulfides enter the story. As certain bacteria process organic material without oxygen, they use alternative chemical reactions that produce hydrogen sulfide. To most animals, this compound is a problem. It interferes with respiration and disrupts cellular function. But in the deep sea, it is also a source of energy. Chemosynthetic microbes exploit sulfide the way plants exploit sunlight. Through specialized metabolic pathways, they convert chemical energy into biological material. Carbon is fixed into organic molecules, forming the base of a food web that operates entirely without light. This is not photosynthesis with a different name. It is a fundamentally different strategy for life. The chemistry of decay creates gradients. Concentrations of sulfide, oxygen, and other compounds vary over small distances, forming invisible landscapes that organisms navigate with precision. Some position themselves where energy is abundant, but conditions are harsh. Others settle at the edges, trading lower energy availability for greater safety. These chemical maps define where life can exist and how it behaves. What makes this system remarkable is its efficiency. Very little energy is lost. Compounds released by one process become inputs for another. Waste, in one context, is fuel in another. The entire system operates like a closed loop, recycling matter until almost nothing usable remains. This chemical choreography is slow but persistent. Reactions that would proceed rapidly at the surface unfold over years in the cold, deep sea. This slow pace extends the availability of energy, allowing ecosystems to persist long after the initial input. Decay here is not an ending, it is a long-term investment. Understanding this chemistry has reshaped how scientists think about life's requirements. Light, once considered essential, is revealed as optional. What matters is energy, and energy comes in many forms. At food falls, chemical potential replaces sunlight, and life adjusts accordingly. There is also a philosophical shift embedded in this realization. Decay is often framed as destruction, the opposite of creation. In the deep sea, decay is creative. It builds ecosystems. It fuels growth. It sustains communities that would otherwise have no source of power. So when we talk about the chemistry of food falls, we are really talking about an alternative version of life's playbook. One where vibes are replaced by reactions, and darkness is not an obstacle, but a constant. In this world, chemistry is not just background, it is the main character. When a whale dies and sinks into the deep ocean, It feels like the end of a story. A life concludes, a body disappears from view, and the surface world moves on. But from the planet's perspective, this is not an ending at all. It is a transaction, a transfer of carbon from one account to another, logged quietly in Earth's long-term balance sheet. Carbon is the currency of life. Every living organism is built from it, and every ecosystem is shaped by where carbon goes. How long it stays there, and how fast it moves. At the surface, carbon cycles rapidly. Organisms grow, respire, die, and decompose. Much of that carbon returns to the atmosphere quickly, continuing a fast loop that influences climate on short timescales. The deep ocean operates on a different rhythm. When carbon sinks into the abyss, it slows down dramatically. Food falls are one of the most direct ways large amounts of carbon make that journey from the surface to the seafloor. A whale's body contains tons of carbon accumulated over decades of feeding. When it sinks, that carbon is removed from the surface system and delivered to a place where exchange with the atmosphere is minimal. This process is part of what scientists call long-term carbon sequestration. Carbon locked away in the deep ocean can remain there for centuries or longer, especially if it becomes buried in sediment or incorporated into slow-cycling biological processes. From a climate perspective, this matters. Carbon that is not in the atmosphere is carbon that is not trapping heat. Food falls contribute to this sequestration in several ways. Some carbon is consumed and respired by deep-sea organisms, entering the local carbon cycle, but remaining far from the surface. Some is incorporated into biomass, extending its residence time, and some becomes buried in sediment, effectively removed from active cycling altogether. Each pathway slows the return of carbon to the atmosphere. Whale falls are particularly effective at this because of scale. A single sinking whale represents a massive, concentrated pulse of carbon delivered directly to the deep sea floor. Unlike smaller particles that may be consumed before reaching great depths, a whale almost always makes it all the way down. Gravity ensures delivery. The deep sea receives the full package. Over geological time, this adds up. For millions of years, large marine animals have transported surface carbon to depth through their deaths. This process has quietly contributed to the regulation of Earth's climate, acting as a natural carbon pump. It is not flashy, it does not make headlines, but it works. The removal of large whales from the oceans during industrial whaling disrupted this system. Fewer whales meant fewer large food falls, and therefore less carbon delivered to the deep sea through this pathway. While this is only one component of the global carbon cycle, it highlights how biological processes and climate are intertwined in unexpected ways. Food falls also influence carbon cycling indirectly by supporting deep-sea ecosystems that process and store carbon over long periods. The organisms that grow around these sites incorporate carbon into their bodies, sediments, and chemical products. Even after the visible ecosystem fades, the carbon remains, redistributed, but not returned to the surface. What makes this especially fascinating is the timescale mismatch. Human actions influence atmospheric carbon over decades. Food falls influence deep ocean carbon over centuries. These are different clocks ticking in the same system. Understanding both is essential if we want a complete picture of how Earth regulates itself. There is a certain irony here. The death of a whale, often framed as purely tragic, also represents a contribution to planetary stability. This does not diminish the loss of life, but it adds depth to the story. Nature is capable of holding multiple truths at once: loss and function, endings and balance. Food falls remind us that climate regulation is not just about forests and ice caps. It is also about dark, silent processes happening far below the waves. Processes that depend on life, death, and gravity doing what they have always done. In the deep ocean, nothing is wasted, not even carbon. For most of Earth's history, ocean food falls were governed by natural rhythms. Whales lived, fed, migrated, and eventually died, delivering their immense bodies to the deep sea with quiet regularity. The system was not predictable on short timescales, but over millions of years. It was reliable enough for entire ecosystems to evolve around it. Then humans arrived with harpoons, engines, and a talent for disrupting things they could not see. Industrial whaling in the 19th and 20th centuries removed an enormous amount of biomass from the oceans. Tens of millions of large whales were killed in a relatively short span of time. The immediate impacts were obvious at the surface: collapsing whale populations, altered food webs, and the loss of some of the largest animals to ever exist. What went largely unnoticed was what this meant for the deep sea. Fewer whales at the surface meant fewer whales dying naturally, and fewer natural deaths meant fewer large food falls reaching the sea floor. This was not a gradual change. It was a sudden drop in a resource that deep-sea ecosystems had depended on for evolutionary timescales. Imagine removing a critical seasonal event from an environment and expecting nothing to notice. The deep sea noticed. Communities adapted to exploiting whale falls would have experienced longer gaps between opportunities. Populations reliant on these events may have declined or been forced to shift strategies. Some specialized species likely disappeared entirely, leaving no fossil record and no human witnesses. Extinction in the deep sea does not come with announcements. This impact is difficult to measure directly because the deep ocean is hard to observe and baseline data from before industrial whaling is limited. But the logic is clear. Remove a major energy input, and the systems built around it change. Food falls are not luxuries in the deep sea. They are keystones. Modern conservation efforts have begun to reverse some of this damage. Many whale populations are recovering, slowly rebuilding their numbers. This recovery is often celebrated for surface-level reasons: biodiversity, ecosystem balance, and ethical responsibility. Less often discussed is the quiet revival happening far below, as the potential for large food falls increases once again. However, recovery is uneven. Some species remain critically endangered. Others face new threats from ship strikes, noise pollution, and climate-driven changes in prey availability. Conservation is not just about preventing extinction. It is about restoring processes. Food falls are one of those processes. Human activity also affects food falls in more subtle ways. Climate change alters ocean temperatures and circulation patterns, which can influence where whales feed and migrate. These shifts may change where food falls occur, redistributing deep-sea resources in ways that ecosystems are not adapted to handle. The map of opportunity may be redrawn. There is also the issue of human-generated organic falls. Shipwrecks, discarded fishing gear, and other debris introduce new materials to the seafloor. While these can provide hard surfaces or temporary resources, they do not replicate the chemical or energetic value of biological food falls. Not all inputs are equal, and the deep sea can tell the difference. Understanding human impacts on food falls forces us to confront an uncomfortable truth. Our influence extends far beyond what we can see. Decisions made at the surface ripple downward, affecting ecosystems operating on timescales and spatial scales that dwarf our own. The deep sea is not insulated from human history. It is archived in it. The idea that fewer whales mean fewer deep-sea dinner invitations may sound humorous, but it captures a real ecological consequence. Invitations that went unanswered changed lives, changed evolutionary trajectories, changed the chemistry of the seafloor. As conservation science advances, there is growing recognition that protecting large marine animals protects far more than their immediate surroundings. It protects processes that link surface and depth, life and death, present and future. Whale recovery is not just a win for whales. It is a delayed but meaningful gesture toward ecosystems that have been waiting in the dark. In the deep sea, recovery is slow, but memory is long. At some point in the study of ocean food falls, scientists reached an inevitable conclusion. If you want to understand what happens when something big dies in the deep sea, sometimes you have to help it along. Waiting for nature to cooperate is admirable, but it is also wildly inefficient when your research subject appears without warning, sinks anywhere it wants, and then vanishes into a pitch-black landscape the size of a continent. So researchers did what scientists do best. They started dropping things on purpose. Artificial food fall experiments are exactly as strange as they sound. Large carcasses, often whales that died from natural causes or strandings, are carefully transported offshore and lowered to the seafloor under controlled conditions. The goal is not spectacle, it is consistency. By choosing the location, depth, and timing, scientists can observe processes that would otherwise be nearly impossible to study systematically. These experiments require meticulous planning. A multi-ton carcass does not politely sink straight down. It drifts, it twists, it catches currents. Engineers and biologists work together to ensure the body reaches the intended site intact. This is not a casual operation. It is closer to underwater logistics, mixed with marine biology and a dash of existential reflection. Once the carcass reaches the seafloor, the real waiting begins. Remotely operated vehicles and deep-sea observatories are used to monitor the site over months and years. Cameras capture who arrives, when they arrive, and how they interact. Sensors record chemical changes, temperature shifts, and sediment disturbances. The entire process is documented patiently, because in the deep sea, nothing happens on a human schedule. What these experiments have revealed is invaluable. Controlled food falls allow scientists to track ecological succession with precision, observing how communities assemble over time, instead of piecing together fragments from chance discoveries. Researchers can watch the story unfold, from the first arrival to the final fade-out. Artificial food falls have also uncovered surprises. Some species arrive faster than expected. Others never show up at all. Patterns emerge that challenge assumptions about dispersal, competition, and resource use. These experiments act like stress tests for ecological theory, revealing which ideas hold up when exposed to real-world complexity. There is also a technological side to these studies. Advances in deep-sea imaging, robotics, and long-term monitoring have transformed what scientists can observe. Cameras now capture interactions that were once purely speculative. The deep sea, while still remote, is no longer entirely out of reach. Of course, deliberately placing carcasses on the seafloor raises ethical and logistical questions. Researchers are careful to minimize disturbance and ensure that materials introduced are natural and appropriate for the environment. The goal is to study processes that already occur, not to create artificial ecosystems that would never exist otherwise. In a way, these experiments are acts of translation. They take a hidden process and make it observable. They allow scientists to tell stories backed by evidence rather than inference. Without them, much of what we know about food falls would remain hypothetical. There is also an element of humility involved. Dropping a carcass into the deep ocean does not guarantee understanding. Nature still controls the outcome. Scientists can observe, measure, and analyze, but they cannot dictate how life responds. The deep sea remains stubbornly autonomous. The image of scientists patiently watching a carcass for years may seem absurd, but it reflects a deeper truth about science itself. Some questions cannot be rushed. Some answers require waiting in the dark, gathering data slowly, and accepting that insight arrives on its own terms. Artificial food falls are not shortcuts. They are commitments. Commitments to long-term observation, to curiosity without immediate reward, and to understanding systems that operate far beyond everyday experience. In the end, these experiments have done more than expand knowledge. They have reshaped how we think about the deep sea, not as a static void, but as a dynamic, responsive world, where even the most unusual experiments reveal familiar patterns of life, adapting, competing, and persisting. And yes, somewhere out there, a scientist is staring at a screen, waiting patiently for something to crawl onto a skeleton, and loving every minute of it. Evolution in the deep sea moves at an unusual pace. On one hand, the environment is stable. Temperatures barely change. Day and night do not exist. On the other hand, resources are scarce and unpredictable. This combination creates a strange, evolutionary landscape, one where life is not constantly reinventing itself, but when opportunity appears, adaptation accelerates. Food falls are where that acceleration happens. A food fall is not just a meal, it is an extreme event in evolutionary terms. It introduces a sudden, localized surge of energy into an environment defined by limitation. For organisms capable of exploiting it, the payoff is enormous. For those that cannot, the opportunity passes unnoticed. This sharp contrast acts as a powerful filter, favoring traits that allow rapid detection, efficient use, and survival under unusual conditions. Over time, repeated exposure to these events selects for specialization. Generalist strategies that work in the background of the deep sea are often insufficient at food falls. Here, competition is intense, chemistry is challenging, and timing is everything. Species that evolve, traits tailored to these conditions, gain an advantage, and those traits become refined across generations. This is where food falls function as evolutionary pressure cookers. They compress selective forces into short windows, amplifying their impact. Traits that might take much longer to evolve under steady conditions can be favored quickly when survival hinges on exploiting a rare event. The deep sea may be slow, but selection at food falls is not. One of the most striking outcomes of this process is the emergence of extreme specialization. Some organisms evolve life histories that revolve almost entirely around food falls. Their morphology, physiology, and behavior are tuned to a narrow set of conditions. This level of specialization would be risky in a more predictable environment. But in the deep sea, where alternatives are limited, it can be surprisingly effective. These evolutionary pathways also promote diversification. As species adapt to different aspects of food falls, they reduce direct competition. One lineage may specialize in early arrival, another in chemical tolerance, another in long-term persistence. Over time, these differences can become pronounced enough to drive speciation, increasing biodiversity in an environment often assumed to be uniform. Food falls also influence evolutionary innovation. The unusual conditions they create favor novel solutions. Symbiotic relationships, unique metabolic pathways, and unconventional feeding strategies all find fertile ground here. Traits that might be disadvantageous elsewhere can thrive when the rules change temporarily. Importantly, these evolutionary effects accumulate over vast timescales. Whales and other large marine animals have existed for millions of years. Their deaths have repeatedly introduced food falls into the deep sea, creating a consistent, if unpredictable, selective force. Evolution responds not to individual events, but to patterns. And the pattern here is clear enough to leave a lasting mark. This perspective challenges the idea that the deep sea is an evolutionary backwater. Instead of being a place where change is slow and minimal, it becomes a landscape shaped by episodic intensity. Long periods of stability are punctuated by moments of extreme opportunity, and evolution takes full advantage. Food falls also highlight the interconnectedness of evolution across environments. Traits favored at these sites may influence survival elsewhere, and vice versa. The deep sea is not isolated from evolutionary processes at the surface. It is part of a continuum, linked by gravity, chemistry, and time. In the end, the role of food falls in evolution is about opportunity meeting constraint. They provide energy where there is little, complexity where there is simplicity, and pressure where there is stability. Under these conditions, life does what it has always done. It adapts, it specializes, it finds a way. In the harshest neighborhood on the planet, food falls are the places where evolution works overtime. Chapter 20. A reflective conclusion, tying death to life in the deep ocean, ending with the idea that even in the darkest depths, nature wastes nothing and always cleans its plate. Far below the waves, beyond the reach of sunlight and sound, the deep ocean carries out one of the most honest bargains in nature. Nothing is free, nothing is wasted, and everything eventually becomes something else. Food falls are the clearest expression of that bargain. They are where endings are converted into beginnings, and where death quietly becomes the engine of life. What makes this process so powerful is not its drama, but its consistency. A body sinks, life responds, energy moves. Over and over, across millions of years, the same story plays out with infinite variation. There is no ceremony, no pause for reflection. The deep sea does not mourn, it repurposes. In this world, death is not a failure state. It is a feature. It is a delivery mechanism, a redistribution of resources, a way of keeping life moving in a place where movement is otherwise rare. Food falls remind us that ecosystems are not just shaped by growth, but by loss. Without endings, there are no openings. There is also something profoundly democratic about it. No matter how large or powerful an organism is in life, in death it becomes shared. A whale that once dominated the surface ocean becomes nourishment for creatures it never encountered, in a realm it never visited alive. Energy flows downward, crossing boundaries that life itself could not. This challenges how we think about importance. In the deep sea, significance is not measured by visibility or dominance, but by contribution. A carcass does not need to persist forever to matter. It only needs to arrive. From there, the system takes over. Food falls also offer a quiet counterpoint to human anxieties about waste. On the seafloor, there is no concept of leftovers. Every molecule is used, transformed, and passed along. What cannot be consumed immediately is stored, recycled, or slowly released. Time is generous. Efficiency is absolute. There is comfort in that idea. In the darkest, most remote parts of the planet, life has solved the problem of scarcity, not by abundance, but by patience, by waiting, by being ready when the moment comes. It is a strategy that has worked for millions of years, without planning, without intention, without complaint. As we surface from this journey, it is worth remembering that these processes continue, whether we are watching or not. Every day, somewhere in the ocean, something sinks. Somewhere else, life gathers. Somewhere else still, chemistry hums along, turning loss into possibility. Food falls are not anomalies. They are reminders that life is resilient, adaptable, and deeply interconnected. Reminders that death is not the opposite of life, but part of its rhythm. And reminders that even in places defined by darkness and pressure, nature remains astonishingly efficient. In the deep sea, the plate is always clean,